today. All right, so starting on page 90, we'll take our quick look at the calendar. Today is our second day of applications of systems. That is to say, we're doing more word problems today. The word problems today are going to be a little bit tougher than the ones yesterday, but the table hopefully will still help us organize all of that information. Coming up on Wednesday is our review day for test number 1, which is on Friday, last day before spring break. It was our first of 2 tests. And that test is on everything from the semester. Questions on the calendar? Okay, so then starting at the top of page 90, Ben, the summary.
This lesson we continue to look at
Thank you. Tyler, number 1. Okay, so this is a new kind of problem. It's a mixture kind of problem, and you've got these 2 different strengths of antifreeze. Antifreeze is basically just this chemical called glycol with some water. So depending on how much of that chemical you use, you can make the antifreeze stronger or weaker. And so it turns out that the 2 kinds of antifreeze that this mechanic has are a 20% of that chemical, and then the other 80% is water, or a 35% of the chemical, and the other 65% is water. All right. So that second one is the stronger one. But he doesn't want either of those concentrations. He wants a 25% glycol solution, the other 75% being water, and we want to make 12 quarts altogether. Okay, so would you guys buy that there's probably some way to mix these 2, the 20 and the 35, to get a 25% when all is said and done? If I were after a 40% solution, could I mix a 20% and a 35% and build a 40? No, right? But any number between 20 and 35, we should be able to get. So let's see if we can get that to the 25. And before we do, just one quick warm up. Suppose that the entire 12 quarts are made from the 35% glycol solution. How would you find out how many quarts were glycol? 12 times 0.35. I buy that? All we would do is find 35% of 12. And that number would tell us how much of the 12 quarts were glycol and tell us the number of quarts. All right, so that I cannot do in my head. So how about I say we try the 20%, all 12 quarts being the 20%. So I think that's 2.4. So if we had 12 quarts entirely of that 20% solution, then we would do 20% times the 12. And that would tell us that 2.4 quarts out of the 12 were this chemical glycol, and the rest of it is water. Fair? Okay, so the question is how much of each bottle, each of the 20 and the 35% bottles, should be in the mixture. We're going to pour some unknown amount of each of these together. So those are our 2 variables. L will be the amount of antifreeze in quarts at the 20% concentration. I chose L for low and H for high. So the higher concentration one is H. And then we've got a very familiar looking table. The first column is how much stuff you have, how much antifreeze altogether. Again, remember the word antifreeze means this chemical glycol with water. That's all that antifreeze means. So we've got L quarts of the low stuff and H quarts of the high stuff, and the final mixture or the total is supposed to be 12 quarts. And then we got the percent that's glycol. Notice that just like Ben said, we're going to change those percentages to decimals. And if we're going to use them, we got to get them to be decimals. So the first one is our 20%. The next one is our 35%. This might be the first time that we actually have a number in the bottom middle here. I don't know if we had a number in that spot in any of the tables last time. But 25% glycol is the desired mixture. And then in all of the tables last time, what did we do to the first 2 columns to get the last column? We multiplied. All right, let's see if multiplying feels reasonable in this problem. What we're after is how much glycol we have in quarts. What's the difference between amount of antifreeze and amount of glycol? Glycol is what? What were you going to say? Yeah, so the glycol is just part of the larger antifreeze, right? Again, antifreeze is this glycol plus water. So remember right up here, if we were making 12 quarts and it was all the 20% solution, then multiplying those two things told us how many quarts of glycol we had, yeah? And so if we take our 20% now, not times 12 quarts, but times some unknown number of quarts, some generic number of quarts, then multiplying those together seems reasonable, yes? Okay, and so then we do the same thing here, 0.35 times H, that tells you how much glycol you have from the high concentration stuff. And then we actually keep going. I don't think we did this last time either, but we've got numbers in the bottom row here, so let's multiply those numbers. 12 quarts, it's supposed to be 25% glycol, so we multiply them. This is a mistake that I made. Can you guys cross that off? 12 times 0.25 is 3, not 4. And that 3 means something in this problem. What does it mean? That's it, the total amount of glycol in the final mixture. We better have 3 quarts of that chemical. Great. Okay. So we're going to get our equations in the same way that we got them last class. Can somebody read the equation from that first column? L plus H equals 12. Everybody buy that? Add the two things together, get 12. That's that bottom equation. And somebody else read the equation from the last column. That's true, but I'm looking for an equation that takes everything, every one of those cells into account. Want to try again? It's like the L plus H equals 12. Everybody buy that? That's saying you're going to take the amount of glycol you get from the low concentration plus the amount you get from the high concentration, and it better equal the 3 quarts of glycol that we're after. And that's right there. Okay, and then all of a sudden it's a familiar looking system of equations. You can use substitution or elimination to solve it. I think I might have said this last time, but just one possibility, because a lot of the problems today will involve percentages, which involve decimals. You could multiply both sides by what number to get rid of all those decimals? Yeah. If you multiply both sides of that blue highlighted equation by 100, it takes the decimal points and moves them 2 places to the right. So that 0.20L becomes 20L plus the 0.35L H becomes 35H. 3 becomes 300, everything times 100. And if that is more friendly for you because you don't want to play with the decimals, then know that you can do that. Okay, so just like last time, we're not going to spend our time together solving the system. I just wanted to make sure we can set it up. I've got my answer here. You can check it later on if you want to try solving it on your own. Okay, number 2 is the other kind of problem we'll talk about today. Christian? Okay, so folks are familiar with this rate times time equals distance. If you travel 60 miles an hour for 3 hours, how far did you go? 180 miles, yeah. The rate of 60 times the time of 3 gives you the distance, 180. Okay, so we'll use that equation. Let's go to 3. Jeremy? Irma? Irma? Okay, so we've got this plane trip we're going to make, and the plane normally flies however fast it flies, and the wind normally does its thing, And if the wind and the plane are working together, then the plane gets to go faster than it normally would, right? But when the plane goes back, if the wind is now going the same way, then they're working against each other and the plane is going to go slower than it normally would. So we're going to try to find the speed of the wind and the speed of the plane if there weren't any wind. So those are going to be our two variables. W is the speed of the wind in miles per hour, and P is the speed of the plane in miles per hour. That's in still air. And then we're going to fill in with brand new headings. So this looks different now from all the tables that we've had before about rate and time and distance. And if we put them in that order, then what do we do to the first two columns to get the last column? We're going to multiply them because of that formula we just saw, rate times time equals distance, right? Okay, so let's look at the middle column first. That's the easiest one. So it says the trip to Saratoga when we went with the wind took 3 hours, so that's the 3. And then return trip against the wind took 5. So we got 3 and 5, right? Okay, it's the first column that's the tough one. Let's pick up some numbers. For example, suppose that the plane normally travels 50 miles an hour. It's a very slow plane. And the wind is 10 miles an hour. If they are working together, then how fast is the plane really going? 60. And if they're working against each other, how fast is the plane really going? It's not flying at 50 anyway, but just go with me here. How fast is it going if they're going against each other? It's 40. Everybody okay with that? So then if I wanted to, like, how did you guys get 60 when they were working together? You added them, right? The 50 plus the 10. So P plus the W is what you did when they were working together. That was the 60. And what did we do when they were working apart against each other? As we subtract them. W minus P or P minus W? The plane minus the wind, right? P minus W. And those are the things that go into the rate column. When they work together, P plus W. When they're opposing each other, P minus W. All right, so that's the toughest part. I think the rest is going to be pretty straightforward. Like we've seen before, when you want to get the last column, we multiply the first two. The way we've set it up, we can continue to do that. Rate times time is distance, so 3 times P plus W is here, and then 5 times P minus W is there. And then we need our two equations. And the two equations, you can see there's no total row. There's no bottom row here like before. But we know the distances. How long was the distance between Saratoga and, it's 450 miles. So this 3 times P plus W is going to equal 450. And this one is also going to equal 450. It's the same distance regardless of which direction. Yeah? Okay, so those are our two equations down there. They look a little bit different, but if you distribute the 3 and the 5, then they will look quite similar to all the equations we've been solving over the last few classes. Yeah? Okay, so again, we're not going to spend our time solving them, but you can check the answer later on. It's down below. Okay, just a couple of common errors I wanted to highlight. Can we go to Ramses? Start here with this also. Let's pause right there. So if you're not careful, you might put the P plus W in the wrong row. So how do you know which row to put it in? Well, you made a choice to put the times somewhere. So if we're doing something in 3 hours compared to 5, where does the trip with the wind go? Is that with the 3 or the 5? Yeah, with the wind is the 3, but it's really easy to get that one backwards, right? If you have the wind working with you, then your trip takes less time. And so you got to make sure you put the P plus W with the smaller time. All right, Ramses, keep going. Okay, yeah, so we said P minus W and not W minus P. It's always the plane minus the wind. All right? Okay, activities start on the next page. Just like yesterday, you're going to have a ton of word problems to do today. So let's see if we can get through all the activities and all of the even more practice. And raise a flag if you get stuck.